Good day, class. We will be discussing regarding threaded members. So we just do add-ons for this. So previously we already discussed some of the terminologies in threaded members. So we'll just a recap. So threaded members, as already discussed, that these are the components with ridge or thread can be allowed to screwed corresponding to a threaded part. So these are commonly used in construction, automotive, machineries, and other industries where two parts are needed to be joined securely, but can be separated in the latter part. No, so these are bolts, and bolts are typically used with the knot, and as they two pass unthreaded holes in the parts, they are secured in tightening the knot on the opposite angle. No, so they are used for meat. They be using knots, bolts and nuts. No, and other type of the threaded members are screws. So screws are designed to be screw directly into a material or a pre-threaded hole, no, in order for you to have a stronghold. But screw doesn't need a knot like the bolt, no. So as it is, no, you can uh you can insert the screw without a knot. Okay, and these are type of threadeds. No, we have the unified national cores, you have the unified national fine, you have the unified extra fine, and then the unified 8 series. So the UNC is a type of thread for general usage. So for the UNF, this is specifically used in automotive and aircraft work. For the extra fine, these are used for aeronautical equipment. And the last one, which is the unified 8 threads, these are for high pressure pipe flanges, cylinder head, studs, etc. So uh the basic parts of the threaded members are the major diameter, the minor diameter, the pitch diameter, the lead, the root, angle of thread, you have the pitch, you have the crest, no? So of course, major diameter would be the largest diameter of the thread or the knot. The minor diameter would be the smallest, and the pitch diameter would be the mean diameter of the major and the minor diameter. So lead is the actual distance between the points adjacent threads on adjacent threads, and then the root would be the bottom surface joining the sides of the two adjacent threads. And then, of course, the threaded angle or the angle of thread would be the angle between the sides of the thread. And other terminologies are given to your handouts. Okay. So we have the type of bolts. We have the machine bolt, the eye bolt, the stud bolt, and then we have the U bolt, and then the slope bolt. Okay. So I already gave you also the definition of those these bolts, no? And for a standard form of threads, we have the Acme threads, or the modification of the square form thread, the V thread, used for watchmaker, no? Square thread would be for threads which is equal, no? The brown and sharp worm thread are cut deeper, and then the buttress would be slanting on the other side. So uh the reading for bolt specification number by an American Unified Series example. So this is 14 dash 20 UNC dash 2A. So 1/4 represents the nominal size in inches. 20 represents the thread per inch. And of course, UNC, the Unified National Course. 2 would be the tolerance, and A would be the external thread. And for also another example, by unified series also. So you have the nominal size in inches, the thread per inch, the unified natural fine, tolerance, and internal threads. Okay. So these are some of the formulas. I already gave some. We just add this one. And these are some of the easy problems. So if the pitch of the screw is 4/9, find the thread per inch. So the solution would be 1 over the pitch, or TPI would be the thread per inch, 1 over 4/9, and the TPI would be 2.25 inches. And then the sample problem, what is the working strength of a 2 inches bolt, which is screwed up tightly in package joint when the allowable stress is 12,000 PSI. So you have the formula, uh, the strength, sorry, ST, which is 12,000 PSI. Then you just do the uh, 0.55 times 2, the diameter is 2 inches, and then that would be the weight. Okay. And for of course, the importance of a threaded member differs in various application, no? With their respective ability to secure adjusting and then reusing the connection. So you have strength and stability. So threaded fasteners like bolts and screws provide small strong connections, which is significant, can withstand significant forces, no? And this is ideal for heavy duty application in construction and automotive and aerospace industries. And also another one would be the ease of assembly and disassembly. So like what I told you, it can allow for parts to be easily joined and separated without damaging the components. So this is particularly useful in maintenance, repair, or replacement if necessary. So the next importance of threaded member is precision and control. So threads on fasteners will allows you for precise control over the tightness, yung connection of the connection, enabling fine adjustments, and ensuring application instability application. Okay. So the other um importance is that it is versatile, no? It is the threaded member varies in um in a variety of sizes, materials, depending on the suits to different application, from small electronics to large structural frameworks. So the versatility is widely applicable in not just in mechanical engineering, but to other engineering fields or uh, other professions. So this is reusable. The other importance, this is reusable. Not like other joining methods. This joining methods can be reused. Um, and also it also gives you cost effectiveness and sustainability in the long run. Okay, then also the another importance is load distribution. So by clamping parts together, it helps you distribute loads evenly across connected components, and it reduces concentration uh, to help the distribution of the loads eventually. Okay, so these are some of the importance, no, of a threaded member. So it is it is widely range, no, application for the threaded member. And also the application, of course, like what I told you, it could be used in construction infrastructure, such as the building, no? Building, yes, building, And also joint beams, no, you can also have that. So you have construction, you have also of course the automotive industry, and then also for aerospace. You can also use that in electronics and appliances. You can also of course manufacturing industry. uh Such as of course it's used for disassembly, for maintenance also, and replacement. CNC machines, presses, conveyor systems, that are the applications uh for screws. Now of course we have the furniture and woodworking for components like shelves, doors, etc. Medical devices and equipment. So like the surgical tables, hospital beds, diagnostic machines, fasteners allow for easy maintenance and adjustments with respect to reliable operation on in medical environments. Of course, the oil and gas industry. So oil and gas, we are using this as a viable or a vital role in leak proofing connections, which is critical in extreme environments. So, like in the pipelines, drilling equipment, heavy machineries, these are all applied. These are all used by screws, bolts, and nuts. No? Of course, the renewable energy. So the renewable energy, such as, of course, the wind turbines, the solar, the panel mounts, and also other renewable energy. Uh, the fasteners ensures the stability in outdoor environments. So where wind, vibration, and weathering can affect structural integrity. So the ability to assemble, disassemble, and reassemble threaded components makes them invaluable in applications requiring durability, repairability, and flexibility. So it has spanning diverse fields from everyday products to complex industrial systems. So this are the versatility uh of your threaded fasteners. No? Okay. So we solve another problem. So the problem would be uh let me wait for a while. So a square single thread jack screw has a thread 3 threads per inch. So it is to lift 15 tons. So if it's 15 tons, we will use the short tons. So one short tons is equals to 2,000 pounds. So the friction radius of the collar is 1 inch. So the coefficient of friction between the threads of the screw and base is 0.115. That between the screw and the collar is 0.13. So we will to determine the root diameter if the allowable stress and compression is 8,000 psi. The next one is we determine the pitch of the screw. Then we need to find the major diameter, and then the mean diameter, the lead angle, the torque required to overcome friction in threads, and also friction in collar, and then the expected torque, total torque operate in a jack screw, and then the total force operate in a jack screw, and the expected efficiency of the screw. Okay. So for to determine the root diameter, we will be using DR. So DR, or the root diameter, would be square root of 4F over pi S, or the stress, sorry. So square root of 4. F would be, of course, the 15 tons. So we will be uh, converting that. So 15 tons, or the short tons, would be uh, 2,000 pounds. Okay, over pi. And then the compression is 8,000. Okay. So that would be the root diameter. So we calculate that. So 4 times 15. 4 times 15 times 2,000 pounds divided by pi times 8,000 pesos. So that would be the root diameter would be 4.77 inches. Then that would be the root diameter. So next would be, we determine the pitch screw. Okay. So pitch screw would be the pitch of the screws. So we have 1 over the threads per inch. So you have the pitch. So pitch would be 1 over the threads per inch. So that would be 1 over 3, which is given, the threads per inch. So that would be 1 over 3 is equals to 0.33. So the pitch diameter would be 0.033. 0.33. So we already have the pitch. Then next we will calculate the outside diameter. So the DO. Okay, so DO, in order to get to DO, would be the root diameter plus the pitch. So we already computed the root diameter, which is 4.77, and then we already calculated 0.33, the pitch, sorry, for 0.33. So we have 4.77 plus point, sorry, okay, okay, 0.33. So that would be 5.1. 4.77 plus 0.33 would be 5.1 each. Okay, so that would be the outside diameter. Then the next would be, we are looking for the mean diameter. So mean diameter, we will be dm. So dm is equals to the outside diameter plus the root diameter over 2. So that would be, that do would be 5.1 plus 5.1 plus r, 4.77 divided by 2. So that would be 4.935. So EN would be 4.935. Okay. So next, we will have the lead angle. So lead angle would be is equals to tan inverse L over pi dm. So L. So that would be sorry for one. So you have tan inverse. So pi over pi dm is how much? 4.93. Then so you calculate the lead angle. So next, we have the torque required to overcome the friction. Okay. In the threads. Okay. So that would be TS is equals to weight, then the N multiplied by tan F. Sorry, the tan angle, tan theta plus F all over 2, 1 minus F tan alpha. So you just do the substitution and you can get the friction in threads. Okay. So that would be next would be the torque required to overcome friction in collar. So you have FC multiplied by the weight multiplied RF. So FC would be for collar would be this one, 0.13. So for the friction in threads, you will use this 0.115. So this one, weight, and then you have the RF. So you just put 1. Sorry, the coefficient. Sorry, the friction radius of the collar is 1 inch. 1 inch friction collar. So you have FC 0.13 0.13. Weight is 30,000 pounds. And then RF, which is 1. Okay, then you compute this. Okay, next, you have the total torque. So the total torque would be TC plus TS. So you just compute it.